Now another important method to solve limits is using series expansion. In this method, what we'll do is we'll use series expansion of important functions to evaluate the limits. Now one of the series expansion that we already know is this binomial series expansion, and this is 1 plus x to the power n. Now this is nc0 plus nc1x plus nc2x square plus ncn x to the power n if n is a positive integer. Now if n is not a positive integer and it is not 0, and this x lies between -1 and +1, we can write this series expansion as 1 plus nx plus n minus 1 upon factorial 2 x square plus n minus 1 n minus 2 upon factorial 3 x cube, and this series, it continues up to infinite. Now it is possible to get the series expansion for lot many functions. So if we have any function y equals fx, and if we want to express it as sum of the series, we can use something called as Mclaurin theorem. Now Mclaurin theorem, it says this function fx, it can be approximated by the series which is f0 plus x into f dash 0 plus x square upon factorial 2 f double dash 0 plus x cube upon factorial 3 f triple dash 0, and its general term is x to the power n upon factorial n, and this nth derivative of this function at x equal to 0, and plus this series, it continues. So if we have to find series expansion of any given function, we just need to find the values of f0, f dash 0, f double dash 0 to find the coefficients of this series.
Now the question that comes to my mind is, what is a Maclaurin series and why are we studying it? A Maclaurin series is a smart way to represent a real or a complex valued function fx, which is infinitely differentiable at 0 as the power series, which is fx is equal to f0 plus f dash 0 into x plus f double dash 0 into x square upon factorial 2, and this series, it continues up to infinite, or I can simply write it as summation r varies from 0 to infinite r derivative of f at 0 upon factorial r into x to the power r. Using Maclaurin series, we can express a function as an infinite sum of increasing powers of x using its derivative at 0. Now for the series to work, my function has to be infinitely differentiable at 0. Now say for example, I have a function fx, which is an exponential function, and that is e to the power x. Now what is f0? f0 is e to the power 0, which is 1. Now what is f dash x? F dash x is e to the power x. Now for exponential function, any derivative at 0 will always be e to the power x, and there will be e to the power 0. So in this case, all these values f0, f dash 0, f double dash 0, they are all 1. So I can simply write e to the power x as 1 plus 1 into x plus 1 into x square upon factorial 2, and it goes up to infinite, which I can write as 1 plus x square upon factorial 2 plus x cube upon factorial 3, and it goes all the way up to infinite. So that is the series expansion of e to the power x, and this essentially is your Maclaurin series. So in this case, Maclaurin series basically approximates e to the power x as an infinite sum of increasing powers of x And the series on the right closely resembles the values of e to the power x, particularly closer to 0. Now to illustrate this closeness in approximation, what I'll do is I'll use graphs. I'll draw the graph of e to the power x. Now suppose I take very crude approximation of e to the power x. I'll just consider the first term. Suppose I'll say it is y equals to 1. So I'll draw this line. So y is equal to 1 is very crude approximation of e to the power x. Only at 0, the values are same and there is no other similarity between the given two curves. So what I'll do is I'll include the second term also, and now I'll draw this function which is y equals 1 plus x. Now y equals 1 plus x, it's a straight line inclined at an angle 45 degrees and passing through 0, 1. So if I'll draw this line, now it's my second approximation of e to the power x. Now here, the value at 0 is 0 and the derivative at 0 is 1. So it is better approximation than the first, but still very crude, very different from the given function. If I include the third term, that is, if I'll write y equals 1 plus x square upon factorial 2, which in fact is x square upon 2 plus x plus 1. Now it is nothing but a quadratic equation opening upwards. So the graph in purple is an approximate graph of y equals x square by 2 plus x plus 1. So for this function, the value at 0 is 0, the derivative at 0 is 1, and the second derivative at 0 is also. So it is better than the first two approximation, but still not close enough. What if I include one more term? So if I include one more term, then I can simply write it as y equals 1 plus x square upon factorial 2 plus x cube upon factorial 3. So I'll write it as x cube upon 6 plus x square upon 2 plus x plus 1. So I know it's a cubic function. So if I'll draw this cubic function, now for this cubic function, the value at 0 is 0. All its derivative at 0, like first derivative, second derivative, third derivative, they are all 1. And it is closer to the given exponential function. So Maclaurin series is a close approximation of function, particularly close to x equals to 0. So if I'm given any function fx, which is infinitely differentiable at 0, then I can fairly approximately write this function fx as f0 plus f dash 0x plus f double dash 0x squared by factorial 2 up to infinite. This is how we get series expansions of the given function. And because we are considering terms up to infinite, so this result, it gets pretty close to the function.
Now there are some standard results that we'll be using. This third one is expansion of e to the power x, and expansion of e to the power x is 1 plus x square upon factorial 2, x cube upon factorial 3, and will continue up to infinite. Fourth one is expansion of e to the power x. Now expansion of e to the power x is 1 plus x log a plus x log a whole square by factorial 2, x log a whole cube by factorial 3 up to infinite. Fifth expansion is expansion of log 1 plus x. Now this is x minus x square upon 2 plus x cube upon 3 minus x to the power 4 upon 4 if x lies between minus 1 and 1. Then we have expansion formula for sin x. Now for sin x, this is x minus x cube upon factorial 3 plus x to the power 5 upon factorial 5 minus x to the power 7 upon factorial 7. Expansion formula for cos x, it is 1 minus x square by factorial 2 plus x to the power 4 upon factorial 4 minus x to the power 6 upon factorial 6. I will continue up to infinite. Eighth one is expansion of 10x. Now expansion of 10x is x plus x cube upon 3 plus 2 by 15 x to the power 5 and so on.
Why is the expansion of 10x equals x plus x cubed by 3 plus 2 by 15 x to the power 5, and it goes up to infinite. So what most of the students are interested in, how to get this 2 by 15, because there is no pattern or symmetry which we can identify from the given series. So again, the answer lies in Maclaurin series. So here my function fx is 10x. Now I'll find the value at 0. So what is the value at 0? So 10, 0 is 0. Now I'll differentiate the function. I'll find f dash x, and f dash x is secant square of x. So if I'll put 0, now secant 0 is 1. So that is 1. Now I'll find second derivative, f double dash x. So f double dash x will be, so first I'll need to differentiate this power. So this is 2 secant x, and then it'll be secant of x into 10x. So I can write it as 2 secant square x into 10x. So if I'll put x as 0, now 10, 0 is 0. So answer to this value will be 0. Now I'll differentiate it third time. So triple derivative. So if I'll differentiate it again, so here I'll need to use product rule. So I'll get 2 secant square x. Now the derivative of 10x is secant square x, and then plus, now here 2 10x as it is, and now the derivative of secant square x is 2 secant x into secant x into 10x. So that will simplify to 2 secant to the power 4x plus 4 secant square x into 10 square x. Or I can still simplify it as 2 secant to the power 4x plus 4 secant square x, and I can write 10 square x as secant square of x minus 1. So I'll actually write it as 6 secant to the power 4x minus 4 secant square x. So that's your third derivative. So if I'll put x as 0, I'll get f triple dash 0 as 6 minus 4, and this value will be 2. Now I'll find its fourth derivative, and which will be, so if I'll differentiate this, I'll get 24 secant cube x into secant x into 10x and minus 8 secant x, and it is secant x into 10x. So I'll write it as 24 secant to the power 4x into 10x minus 8 secant square x into 10x. Now if I'll put again x as 0, now fourth derivative of this function 10x at 0, it'll be simply 0 because I have 10x and 10x here. Now I need to differentiate it one more time. Now I'll find the fifth derivative of this function. So again I'll need to use product rule. So there'll be 24 secant to the power 4x, and derivative of 10x is secant square x, and then plus 24 10x, and then derivative of secant to the power 4x is 4 secant cube x into secant x into 10x, and then minus 8. Now here secant square x as it is, and derivative of 10x is secant square x, and then again minus 8 10x, and it will be 2 secant x and then secant x into 10x. So now I'll write its fifth derivative at 0. Now at 0, all these terms containing 10x, they'll be 0. So what I'm left with is, I'll get this is 24 minus 8, and which is 16. So now I have value of this function at 0. I have the value of f dash 0. I have the value of f double dash 0. I have the value of f triple dash 0. I have fourth derivative of this function at 0. And I have fifth derivative of this function at 0. So if I use Mclaurin theorem, I can simply write 10x as f0 plus f dash 0 into x plus f double dash 0 x square upon factorial 2 f triple dash 0 x cube upon factorial 3 fourth derivative at 0 x4 upon 4 fifth derivative at 0 x to the power 5 upon factorial 5, and this series it will continue up to infinite. So now I'll start putting in the values. Now clearly f0 is 0 plus, now f dash 0 it is 1, so there'll be 1 into x plus second derivative at 0 it will be 0, so 0 into x square upon factorial 2. Now triple derivative it is 2, so this is 2 x cube upon factorial 3. Now fourth derivative again it's 0, so this is 0 x to the power 4 upon factorial 4, and now your fifth derivative which is 16 x to the power 5 upon factorial 5, and this series it continues up to infinite. So I can simply write it as simply x plus, I'll be twice x cube, and what is factorial 3? Factorial 3 is 3 into 2 into 1, and plus 16, this is x to the power 5, and this is 5 into 4 into 3 into 2 into 1. So here 2 will get cancelled, and here 4 into 2 is 8, and this 8 it cancels 16, I'll get 2. So I'll get the series as x plus x cubed by 3 plus 2 by 15 x to the power 5, and it goes up to infinite. So it is from this Maclaurin series we can say that this function 10x can be approximated as x plus x cube upon 3 plus 2 by 15 x to the power 5 up to infinite. So this is how we get the series expansion of 10x.
Then we have expansion formulas for sine inverse and tan inverse. Now expansion formula for sine inverse of x is x plus 1 square upon factorial 3 x cube plus 1 square 3 square upon factorial 5 x to the power 5, and so on. Expansion formula for tan inverse of x is x minus x cube upon 3 plus x to the power 5 upon 5, and it continues. We get all these expansions using this Maclaurin's theorem, and it is simple differentiation problem. So if you want, you can verify these results using Mclaren theorem. Now series expansion is one of the easiest and most important method of solving limits. So you must remember all these expansion formulas very well, and if you do that, you'll be able to solve many problems under a minute. Now once we have these series expansion formulas, we can use these formulas to work out other series expansion also. Say for example, we know expansion formula for e to the power x is 1 plus x square upon factorial 2 plus x cube upon factorial 3, and this series it continues up to infinite. Now suppose if we have to find expansion formula for e to the power minus x, so what we'll do is we'll replace x with minus x. So it'll be this 1 minus x plus x square upon factorial 2 minus x cube upon factorial 3, and it'll continue up to infinite. Or suppose we have to find expansion of e to the power x square. Here we'll replace x with x square, so it'll be this 1 plus x square plus x to the power 4 upon factorial 2 plus x to the power 6 upon factorial 3 up to infinite. So using these formulas, we can work out other series expansions also. If we take another example, we know that expansion of log 1 plus x, it is x minus x square upon 2 plus x cube upon 3 minus x to the power 4 upon 4 up to infinite when x lies between minus 1 and 1. Now there is one more expansion formula that we need to study, and which is expansion of 1 plus x to the power 1 upon x. Now we can write this as e to the power log 1 plus x to the power 1 upon x, and it will be this e to the power 1 by x log 1 plus x. Now we already know the expansion of log 1 plus x, so it will be this e to the power 1 by x and then x minus x square by 2 plus x cube by 3 and so on. Now here this x will cancel, so we can write this as e to the power. Now this is 1 minus x by 2 plus x square by 3 and so on. Now we can write this as e into e to the power minus x by 2 plus x square by 3 up to infinite. Now we'll use the expansion of e to the power x. So now we can write this as e, and this is 1 plus x, and x in this case is minus x by 2 plus x square by 3 and plus x square by 2, and that will be minus x by 2 plus x square by 3 whole square upon factorial 2, and then will be higher powers of x. Now we can write this as e into, and this is 1 minus x by 2 plus x square by 3, and here what we need is coefficient of x square, and we'll get this coefficient of x square as x square and then 2 square is 4, and we also have this factorial 2, so there will be this 8 and then other powers of x. So if we write first three terms of this expansion, it will be 1 minus x by 2 plus 11x square by 24, so on and so forth. So this is the expansion of 1 plus x to the power. We'll also be using this expansion formula. Now before learning how do we use these expansion formula and limits, we'll study one standard limit which will be helpful in these series expansion problems. So if we have this limit x tends to 0, a naught x to the power n plus a1 x to the power n plus 1 plus a2 x to the power n plus 2, and this series it continues up to infinite upon b naught x to the power m plus b1 x to the power m plus 1 plus b2 x to the power m plus 2 up to infinite. Now here minimum power of x in the numerator, it is n, and in the denominator minimum power of x, it is m. Now here we have three cases. Case 1, when minimum power of x in the numerator, it is greater than minimum power of x in the denominator. Then in that case, value of this limit, it will be 0. And if n is less than m, that is minimum power of x in the numerator, it is less than minimum power of x in the denominator, then value of this limit, it will be either plus infinite or minus infinite depending on these coefficients. And then we have this third and most important case, when minimum power of x in the numerator is same as minimum power of x in the denominator. So if minimum power of x in the numerator, it is same as minimum power of x in the numerator, that is if n equals m, then in that case value of this limit is coefficient of x to the power m in the numerator and denominator. So value of this limit will be a naught upon b naught. So we'll be using this concept while solving problems using series expansion. Now if we take this example, which is limit x tends to 0, sine inverse x minus tan inverse x upon x cube. Now sine inverse 0 is 0, tan inverse 0 is 0. So first thing, we'll check its form. This is 0 upon 0 form. Now we know the expansion formula for sine inverse, and we also know expansion formula for tan inverse. So we can write this as this limit x tends to 0. Now expansion of sine inverse x is x plus 1 square upon factorial 3 x cube and other higher parts of x, and then minus an expansion of tan inverse x is x minus x cube upon 3 and other higher parts of x divided by x cube. Now here this x and x will cancel. Now in the numerator, minimum power of x is 3 and the denominator minimum power of x is also 3. Now when n is equal to m, value of this limit is coefficient of x cube in the numerator upon coefficient of x cube in the denominator. So value of this limit will be coefficient of x cube in the numerator. Now this is 1 upon factorial 3, which is 1 by 6, and then minus minus plus 1 by 3 upon 1. Now this is 3 by 6, which is 1 by 2. So answer to this limit is 1 by 2. Let us take another example, and which is if this limit x tends to 0, a e to the power x minus b cos x plus c e to the power minus x upon x sin x, it is equal to 2. Find the value of a, b and c. Now in this question also, we see exponential function cos and sine, for which we know the expansion, and this is limit x tends to 0. So we are going to write this as limit x tends to 0, and this is a, and this is 1 plus x square upon factorial 2, which is 2, minus b, and cos x is 1 minus x square upon factorial 2, and plus c, and e to the power minus x is 1 minus x plus x square upon 2 whole divided by x, and this is x minus x cube upon factorial 3, and it is equal to 2. Now what we'll do is we'll write this as ascending powers of x. Now it will be this limit x tends to 0, and our constant term is a minus b plus c, plus this is a minus cx plus 1 by 2 a plus b plus c into x square upon x square minus x to the power 4 upon factorial 3, and it is equal to 2. Now answer to this limit is 2, which is non-zero finite, and it can be non-zero finite only if minimum power of x in the numerator is same as minimum power of x in the denominator. Now minimum power of x in the denominator is 2. That means minimum power of x in the numerator should also be 2. So it simply means that this is 0 and this is also 0. So from here we get two conditions: a minus b plus c equals 0 and a equals c. And basically it is equal to this b by 2. Now when these two expressions, they are 0, answer to this limit is coefficient of x square in the numerator upon coefficient of x square in the denominator. So it will be this 1 by 2 a plus b plus c, it is equal to 2. Now a plus c is 2a, so this is a plus b by 2. So basically value of a and c, it is 1, and value of b is 2. So this is how we use expansion formulae to solve and simplify limits. Now here we are given that this limit x tends to 0, x square sine beta x upon alpha x minus sine x, it is equal to 1. We need to find the value of 6 alpha plus beta. Now we will solve this question using expansion. Now we will write this as x square, and this sine beta x will be beta x minus beta x whole cube upon factorial 3 and higher powers of x divided by, and in the denominator it will be this alpha x minus, and here it will be this x minus x cube upon factorial 3, and we are given that this limit is equal to 1. Now since this limit is x tends to 0 and minimum power of x in the numerator is 3, this limit will have a finite non-zero answer if minimum power in the denominator is also 3. That means this alpha minus 1 into x term, it should not be there in the denominator. So clearly it should be 0. So from here we can find value of alpha is 1. Now if we put alpha as 1, then minimum power in the numerator is 3 and minimum power in the denominator is also 3. So answer to this limit is coefficient of x cube in the numerator upon coefficient of x cube in the denominator. Now coefficient of x cube in the numerator is beta and coefficient of x cube in the denominator is 1 by root 3, which is 1 by 6, and it is 1. So value of beta is 1 by 6. Now we need to find the value of 6 alpha plus 6 beta. Now 6 alpha is 6 and plus 6 beta is 1. So value of this expression is 7, and that is the answer to this question. Now here the question is, we need to solve this limit x tends to 0 log 1 plus x to the power 1 plus x upon x square minus 1 by x. Now we can also write this as this limit x tends to 0 1 plus x log 1 plus x minus x upon x square. Now we'll use the expansion for log 1 plus x. So it will be this limit x tends to 0 1 plus x, and then it will be x minus x square upon 2, and then minus x upon x square now we can write this as x minus x square upon 2 plus x square plus higher power of x minus x upon x square. Now this x and x will cancel. Now this minimum power in the numerator is same as minimum power in the denominator. So answer to this limit will be coefficient of x square in the numerator upon coefficient of x square in the denominator, which is 1 by 2. So answer to this limit is 1 by 2. Now the question is limit x tends to 0 to tan x minus sin x minus x cube upon x to the power 5. Now we'll use series expansion in this. So this is limit x tends to 0, and this is 2, and this is x plus x cube by 3 plus 2 by 15 x to the power 5 minus, now sin x is x minus x cube upon 6 plus x to the power 5 upon 120, and it will be this minus x cube whole divided by x to the power 5. Now x and x will cancel. We'll get this as limit x tends to 0, and this is 2, and it will be this x cube 1 by 3 plus 1 by 6 and plus x5, and it will be this 2 by 15 minus 1 by 120, and then minus x cube upon x to the power 5. Now this is limit x tends to 0, and this is 2 x cube, and it will be this 1 by 2 and plus x to the power 5. It will be this 15 upon 120, and then minus x cube. Now we will take this 2 inside. Now this x cube will cancel. So the lowest power of x in the numerator and denominator, it is x to the power 5. So answer to this limit is 15 by 60, which is 1 by 4. Now here the question is the integer n for which this limit is finite non-zero number. Now this is limit x tends to 0. That means we are looking for lowest power of x in the numerator and the denominator. Now this is cos x minus 1 and this is cos x minus e to the power x upon x to the power n. Now this is limit x tends to 0 and this is 1 minus x square upon factorial 2 minus 1, and here it is 1 minus x square upon factorial 2, and this is minus 1 minus x square upon factorial 2 all divided by x to the power n. Now 1 will cancel and here also this 1 will cancel. Now for this limit to have a finite non-zero answer, minimum power of x in the numerator must be same as minimum power of x in the denominator, as this is limit x tends to 0. Now minimum power in the numerator will be this x square gets multiplied with this x. So in the numerator, smallest power of x is 3. So in the numerator also, smallest power must be 3. That is the value of n, it should be 3, and that's your option C. Now here the question is, we need to find this limit L, which is limit n tends to infinite cos pi into under root of n square plus n. Now we'll take this n square out. We can write this as limit n tends to infinite cos pi into n, and here will be 1 plus 1 by n to the power 1 by 2. Now we'll use binomial expansion. We can write limit n tends to infinite cos n pi, and here will be this 1 plus 1 by 2n, and then it will be 1 by 2 and 1 by 2 minus 1, so it will be minus 1 by 8 n square plus higher powers of n. Now this is limit n tends to infinite cos, this is n pi plus pi by 2, and then minus pi by 8n. Now cos n pi plus theta is minus 1 to the power n into cos theta. So it will be this limit n tends to infinite. Now it will be minus 1 to the power n cos pi by 2 and plus this big notation of 1 by n. Now when n tends to infinite, this is oscillating value, minus 1 plus 1, this is cos pi by 2, and this is simply 0. Now cos 90 is 0 and 0 into oscillating value is 0. So answer to this limit is 0, and that's your option C. Now here the question is, we need to solve this limit. Limit x tends to 0, 1 minus cos x into under root of cos 2x upon x square. Now we'll solve this question using expansion. So we'll write this as limit x tends to 0, 1 minus, and then it will be 1 minus x square upon 2, and this one is 1 minus 2x square upon 2, and that will be 2x square whole to the power 1 by 2. Now again we'll use binomial expansion of 1 minus x to the power n. So it will be this limit x tends to 0, 1 minus, and this is 1 minus x square by 2, and here will be this 1 minus x square upon x square. Now we simplify this, we'll get this as limit x tends to 0, and this is 1 minus, and will be 1 minus minus x square by 2 minus x square. So that will be minus 3x square by 2 and other higher powers of x divided by x square. Now this 1 and 1 will cancel, minus 1 is plus, x square will cancel. So answer to this limit will be simply 3 by 2. Now here the question is, we need to find this limit x tends to infinite cos 2 pi x upon 1 plus x to the power a whole to the power x square if a belongs to R. Now first we'll check its form. Now this is x upon 1 plus x. When x tends to infinite, it will be 1. Now cos 2 pi is 1, and 1 to the power x square is 1 to the power infinite. So it is 1 to the power infinite form. That means we are going to use this shortcut directly. So it will be this e to the power, and then this limit x tends to infinite x square into cos 2 pi. Now we'll actually write this as 1 plus 1 upon x to the power minus a, and then minus 1. Now here we'll use binomial expansion of 1 plus x to the power minus n. So it will be this e, and then this limit x tends to infinite, and then x square, and we can write this as cos 2 pi 1 minus a upon x, and then it will be minus a minus 1. So it will be this a into a plus 1 upon 2 1 by x square, and plus higher power of x, and then minus 1. Now cos 2 pi minus theta is cos theta. So we can write this as e to the power limit x tends to infinite, and we'll take minus common. So it will be this x square 1 minus cos 2 pi a upon x plus other terms. Now we'll rewrite this as e to the power limit x tends to infinite minus x square 1 minus cos 2 pi a upon x. Now we'll multiply and divide everything with 4 pi square, and then a upon x whole square. Now we have to multiply it also. Then will be this 4 pi square a upon x whole square. Now this becomes a standard limit, which is 1 by 2. So we can write this as e to the power, and then this limit x tends to infinite minus 1 by 2 into x square into 4 pi square a upon x a plus 1 upon x square whole square. Now we multiply this x square, we'll get this a square. So it will be this e to the power minus 2 pi square into a square, and that is the answer to this limit. Now here the question is, a circular arc of radius 1 subtends an angle of x radian. As shown in this figure, point C is intersection of two tangent lines at A and B. Let Tx be the area of triangle ABC and Sx be the area of shaded region. Then we have to find Tx, Sx, and this limit. Now radius is 1. If we draw a line here, this angle will be x by 2, and this is 90. And suppose this point is D. So this is A, B, C, and we have this triangle ABC. Now in this triangle OBD, we can write BD as 1 sine x by 2. That means value of AB is 2 sine x by 2. And in this triangle, this angle is pi by 2 minus x by 2. So once we have BD, we can find CD. So we can write BD upon CD will be equal to 10 pi by 2 minus x by 2, which is cot x by 2. So we can write CD as sine square x by 2 upon cos x by 2. Now once we have AB and CD, we can write this Tx, which is area of triangle ABC. So this Tx will be 1 by 2 into 2 sine x by 2 into sine square x by 2 upon cos x by 2. I'll cancel. So we'll get this as sine cube x by 2 upon cos x by 2. Now we'll find Sx, which is area of this shaded region. Now this SXLB. Now area of this sector, which is 1 by 2 r square theta minus area of this triangle, which is 1 by 2 1 square sine x. So it will be this 1 by 2 x minus sine x. Now we need to find this limit Tx upon Sx as x tends to 0. Now this limit x tends to 0 Tx upon Sx will be this limit x tends to 0 sine cube x by 2 upon cos x by 2, and here it is x minus sine x and then into 2. Now we'll solve this question using series expansion. Now it will be this limit x tends to 0, and here will be this x by 2 whole cube upon factorial 3 into 2. Here it is 1 minus x by 2 whole square upon factorial 2, and here will be this x minus x cube upon factorial 3. Now x and x will cancel, it will be this plus, and we have this power 3 here. Now minimum power of x in the numerator is 3 and minimum power of x in the denominator is also 3. So answer to this limit is coefficient of x cube. Now coefficient of x cube in the numerator will be this 2 into and then x upon 2 whole cube. So it will be this 1 by 8, and here it will be 1 into 1 by 6, which is 6 by 4, and that is 3 by 2. So this limiting value is 3 by 2, and that is the answer to this question. Now here the question is, we need to find the value of this limit x tends to 0 cos of sin x minus cos x upon x to the power 4. Now what we'll do is, we'll use the formula for cos c minus cos d. So it will be 2 sine c plus d by 2, and there will be sin x plus x by 2 into sin d minus c by 2. So there will be sin x minus sin x by 2. Now what we'll do is, since it is sin 0 and sin 0, we'll multiply and divide it with x plus sin x by 2 and x minus sin x by 2. We have this x to the power 4, and here will be this x square minus sin square x whole divided by 4. Now this is 1 and this is 1 and this 2 will cancel. So we'll write this as limit x tends to 0 x square minus sin square x upon 2 x to the power 4. Now we'll write this as limit x tends to 0 x plus sin x into x minus sin x upon 2x to the power 4, and we'll use series expansion of sin x. So it will be this limit x tends to 0. Now this is x plus x minus x cube upon factorial 3, and here will be this x minus x cube upon factorial 3 upon 2x to the power 4. Now here x and x will cancel, minus and minus will be this plus. So lowest power of x in the denominator is 4 and lowest power of x in the numerator is also 4. So answer to this limit is coefficient of x to the power 4. Now this is 2x, so it will be this 2 into factorial 3, which is 1 by 6, and then it will be this 2. So answer to this limit is 1 by 6, and that's your option B. Now here the question is, we are given this limit L, and that is limit x tends to 0, and this is a minus, we'll take this a common, and then it will be 1 minus x square upon a square to the power 1 by 2 minus x square by 4 upon x to the power 4 for all a greater than 0. Now this is 0 upon 0 form. So what we'll do is, we'll use series expansion of binomial. So it will be this limit x tends to 0. Now this is a minus, and this is 1 minus 1 by 2 x square by a square, and then plus it will be this n minus 1, and then x to the power 4 upon a to the power 4 divided by factorial 2, and then minus x square upon 4 whole divided by x to the power 4. Now here a and a will cancel, so we can write this limit as limit x tends to 0, and then we have this x square. Now this is minus 1 by 2, and this a and a square, so it will be this minus 1 by 2a minus minus plus, and then minus 1 by 4, and then we'll have minus minus plus 1 by 8 x to the power 4 upon a cube and higher powers of x upon x to the power 4. Now if L is finite, then there should be no x square in this expansion. So this term, it must be 0. So from here we'll get value of a as 2. So value of a, it must be 2, and that's your option A. And if there is no term containing x square, then minimum power in the numerator and denominator is x to the power 4. In that case, value of this limit will be 1 upon 8 a cube, which is 1 upon 8 into 8, which is 1 by 64, and that's your option C. So answer to this question is A and C. Now here the question is, we need to find the value of this limit. Limit n tends to infinite cos square pi, and this is n cube plus n square plus 2n to the power 1 by 3. Now we'll take n cube common, so it will be this limit n tends to infinite cos square n pi, and here it will be 1 plus 1 by n plus 2 by n square to the power 1 by 3. Now what we'll do is, we'll use binomial expansion. So we'll write this as limit n tends to infinite cos square n pi, and here it will be 1 plus 1 by 3n plus 2 by 3n square plus higher power of 1 by n. Now we'll write this as limit n tends to infinite. Now this is cos square and n pi plus pi by 3 plus 2 pi by 3n. Now cos n pi plus theta is minus 1 to the power n cos theta. So it will be this limit n tends to infinite minus 1 square to the power n, and then cos square pi by 3 plus 2 pi by 3n. Now minus 1 square is plus 1, and if we take n tends to infinite, all these terms they will be 0. So this answer will be simply cos square pi by 3, and cos square pi by 3 is 1 by 4. And that's your option C. Now here the question is, we need to evaluate this limit. Now since it has fractional part of x and fraction part of minus x, we need to use left hand limit and right hand limit. Now, if we take its left hand limit, it will be limit x tends to 0 negative sine x minus x square minus fraction part of x, fraction part of minus x upon x cos x minus x square minus fraction part of x into fraction part of minus x. Now, when x tends to 0 negative, we let x as 0 minus h, and we know that fraction part of h is h and fraction part of minus h is 1 minus h. So it will be this limit x tends to 0 negative. Now this is minus sine h minus h square, and then minus, it is 1 minus h into h, and here will be this minus h cos h minus h square, and then minus 1 minus h into h, which is this limit x tends to 0 negative minus sine h. Now this is minus h upon minus h cos h minus h. Now we'll cancel this minus. Now we can write this as limit h tends to 0 positive sine h upon h plus 1 divided by 1 plus cos h, which is 2 upon 2, that is 1. So left hand limit in this case is 1. Now we'll find its right hand limit. Now for right hand limit, it will be limit x tends to 0 positive sine x minus x square minus fraction part of x, fraction part of minus x upon x cos x minus x square minus x minus fraction part of minus x. Here we'll take x as 0 plus h, and then again fraction part of h is h and fraction part of minus h is 1 minus h. So it will be this limit h tends to 0 positive sine h minus h square minus h 1 minus h, and here will be this h cos h minus h square minus h 1 minus h, which is limit h tends to 0 sine h minus h upon h cos h minus h, which is 0 upon 0 form. So what we'll do is we'll use series expansion here. So it will be this limit h tends to 0 positive. Now sine h is h minus h cube upon factorial 3 minus h, and here if we take this h common, cos h is 1 minus h square upon factorial 2 minus h. Now here h and h will cancel, here also h and h will cancel. So minimum power in the numerator is h cube and minimum power in the denominator is also h cube. So answer to this limit is factorial 2 upon factorial 3, which is simply 1 by 3. So in this case, left hand limit is 1 and right hand limit is 1 by 3. So this limit, it does not exist. Now the question is, we need to find this limit x tends to 0 x plus log under root of 1 plus x square minus x whole divided by x cube. Now for this question, what we'll do is we'll take this under root of 1 plus x square minus x as some y. Now if we take this x on the right hand side and square it, we'll get 1 plus x square, and it will be y square plus x square plus 2xy. Now here x square will cancel. We can write x as 1 minus y square upon 2y. Now clearly, when x tends to 0, y tends to 1. So we can write this limit as limit y tends to 1, and here it will be x, which is 1 minus y square upon 2y plus log y upon x cube, which is 1 minus y square upon 2y whole cube. Now we can write this as limit y tends to 1, and this is 1 minus y square plus 2y log y, and here it will be 1 minus y square whole cube into 2y whole square. Now we can write 1 minus y square is 1 plus y and 1 minus y. So we write this as limit y tends to 1, 1 minus y square plus 2y log y upon 1 minus y cube and 1 plus y cube, and here will be this 2y square. Now we don't have a problem with this because here it is 2, which is 4, and here it is 2 cube. So it will be 1 by 2, and this is 0.0 form. So we can write this as limit y tends to 1, 1 by 2 into 1 minus y square plus 2y log y upon 1 minus y whole cube. Now for this, what we'll do is we'll let 1 minus y as h. So it will be this limit h tends to 0, and this is 1 minus h whole square plus 2 1 minus h into log 1 minus h upon h cube. Now this is limit h tends to 0. Now here 1 and 1 will cancel, so we'll get this as 2h minus h square plus 2 into 1 minus h, and we'll use expansion for log 1 minus h. So it will be this minus h square upon 2 minus h cube upon 3 upon h cube. Now if we simplify this, we can write this as limit h tends to 0 will be 2h minus h square, and there will be minus 2h plus 2h square, and then minus h square plus h cube, and then minus 2 by 3 h cube plus higher powers of h divided by h cube. Now 2h will cancel, h square will also cancel. Now minimum power in the numerator and minimum power in the denominator is both 3, and we also have this 1 by 2 which I forgot. So it should be this 1 by 2, 1 by 2 and 1 by 2. So answer to this limit will be 1 by 2, and then coefficient of h cube in the numerator, which is 1 by 3, and the denominator it is 1. So answer to this limit is 1 by 6. Now here the questions, we are given this fx as cos 2x, cos 4x, cos 6x, cos 8x and cos 10x. Then we need to find this limit x tends to 0, 1 minus fx cube upon 5 sine square x. Now f0 is cos 0 5 times, so it will be this one. So it is 1 minus 1 0, sine 0 is 0, so it is 0 upon 0 form. Now we can write this as limit x tends to 0, and we'll write this as 1 minus fx, and here will be f square x plus fx plus 1 upon, and we'll write this as 5x square and then sine square x upon x square. Now this is 1 and this value is 3, so we can write this limit as limit x tends to 0, 3 into 1 minus fx upon 5x square, which again is 0 upon 0 form. Now we'll write this as limit x tends to 0, and this is 3 into 1 minus, now fx is cos 2x into cos 4x into cos 6x cos 8x into cos 10x whole divided by 5x square. Now what we'll do is we'll use expansion formula for cos. So we can write this as limit x tends to 0. Now this is 3. It is 1 minus 2 square x square upon 2. Higher powers 1 minus 4 square x square upon 2. 1 minus 6 square x square upon 2. 1 minus 8 square x square upon 2. And then 1 minus 10 square x square upon 2, and higher powers divided by 5x square. Now we multiply it, then we can write this as limit x tends to 0. This is 3, 1, and then 1 into 1 into 1 5 times, so it will be 1 minus 1, and then we need to find coefficient of x square. Now we'll get x square if this x square gets multiplied with all these ones. Now this is minus minus plus, so it will be plus 2 square upon 2 plus 4 square upon 2 plus 6 square upon 2 plus 8 square upon 2 plus 10 square upon 2 x square upon 5x square. Now here 1 and 1 will cancel. Now minimum power of x in the numerator is x square, and in the denominator it is also x square. So answer to this limit will be coefficient of x square in the numerator and in the denominator. So it will be this 3, and this is 2 plus 8 plus 18 plus 32 plus 50 divided by 5. Now this is 10 and 40, 50. Now this is 10 and 50. So it will be 3 into 110 divided by 5. Now this is 22. So answer to this limit is 66. And that's your option D. Now in question number 5, we are given this limit which is equal to beta. We need to find the value of 6 beta. Now basically, we'll solve this question using expansion. So we can write this beta as this limit x tends to 0, and since in the denominator minimum power is x cube, we'll restrict ourselves to x cube and lower powers. Now e to the power x cube is 1 plus x cube, and we'll discard higher powers, minus, now this is 1 minus x cube to the power 1 by 3, so it will be 1 minus 1 by 3 x cube, higher powers, plus, now here it is 1 minus 1 by 2 x square minus 1, and sine x is x minus x cube upon factorial 3 whole divided by x, and this is x minus x cube upon factorial 3 whole square. Now here this 1 and 1 it will cancel, and here also this 1 and 1 will cancel. Now minimum power of x in the numerator is 3 and minimum power of x in the denominator is also 3. So value of this limit is coefficient of x cube in the numerator upon coefficient of x cube in the denominator. Now coefficient of x cube in the numerator will be 1 plus 1 by 3, and here this value will be minus 1 by 2 upon, and here this coefficient is simply 1. So this value will be simply 6 plus 2 minus 3 upon 6. So value of 6 beta is nothing but 5, and that is the answer to this question.